So let us see a definition of Hausdorff spaces. So a topological space X tau is called a Hausdorff space if for each pair of points x1, x2, now you're taking two points x1 and x2 which are different from each other, so they're a pair of distinct points. There exist neighborhoods u1 of x1 and u2 of x2, so open sets containing each point, such that u1 intersection u2 is the empty set, so they are disjoint neighborhoods of the points. So what is the relation of Hausdorff spaces with convergence? So here is a theorem. So this theorem states that if X is a Hausdorff space, then a sequence xn n in n in X converges to at most one point. So either the sequence does not converge or the sequence converges to one point and one point only. Okay, so here is a short proof of this theorem. So suppose that so let xn and in n converge to a point x in X, and suppose that and let y is a point different than x. Now since x is Hausdorff, this implies that there exists neighborhoods u of x and v of y says that u intersection v is the empty set. However, u must contain all but finitely many xn's because of the condition of continuity, because xn belongs to u for all n greater than or equal to n. So there exists such an n, capital N, after which all the points in the sequence belongs to this neighborhood u, and so it must contain all but finitely many xn's. This implies that we cannot contain, because u and v are disjoint, we cannot contain infinitely many of the xn's, and this means that xn does not converge to y. So we see that when you have a Hausdorff space, the convergence property is nice and you have at most one point of convergence. And now we will go back to our convergence of sequences property and relate it to the continuity of a function. So let us begin with a useful terminology. So this terminology says that if x tau is a topological space, and if there is a metric function d on x such that the metric topology tau d, so this is the metric induced by the metric function, the topology induced by the metric function d, and this is the same as the given topology tau on x, then we say that x is metrizable. So this metrizability of a topological space is an important question, and we will use it in the following theorems, which are about the connection of convergence of sequences and limit points. So connections between convergence of sequences and limit points. So as in the example that we saw for the sequence 1 by n in R, we saw that as xn converges to 0, but also that 0 was a limit point. So let me write 0 is a limit point of the set A, which is 1 by n in n. So if you take the collection of these points xn as a set, then 0 is a limit point, and if you take it as a sequence, then the sequence converges to 0. And this is not a coincidence, as the following lemma will show. So here is the statement of the lemma. So we have a topological space x tau, and A is a subset of x, and we take some point x in the space x. Now if there is a sequence of points in A converging to x, then x is in the closure of A, and the converse holds if x is metrizable. So this is where the metrizability plays a role, and let us see a proof of this lemma. So if there exists a sequence xn such that xn belongs to A for all n in n, and xn converges to x, then taking then any neighborhood u of x has infinitely many xn's. In particular, u intersection A is non-empty, so we just need one, but we have in fact infinitely many, and this implies that x belongs to A closure from one of the theorems about the closure we described before. And for the conversely, if x is a metrizable space with, say, a metric D for the topology on x, and say x belongs to A closure, then we have to show that there exists a sequence xn of points in A converging to A. So how do we find this sequence is the question. So for this we take the point x and we use the metric to have smaller and smaller metric balls around this point. So let us say this has radius 1, then you have another metric ball of radius half, then you have another metric ball of radius 1 by 3, and so on. And for each of them, because since x lies in a closure, for each n in n, we have that the ball of radius 1 over n with center x intersects A at some point. Okay, so let xn belong to this intersection for each n, and now we claim that this sequence xn converges to x. And so for this we just have to show that given a neighborhood u of x, so this is to show that given a neighborhood u of x, there exists a capital N such that xn belongs to u for all n greater than or equal to capital N. So now for a neighborhood u of x, we can find a number epsilon greater than 0 such that the ball of radius epsilon with center x is a subset of u, because these are the basis sets. Now choose n such that 1 over n is less than epsilon. So this means that BD x1 over n is a subset of BD x epsilon for all n greater than or equal to capital N. And because xn belongs to these sets, this means that for all n greater than or equal to n, xn belongs to U. And so we have shown that xn converges to x. So this is the proof of the sequence lemma, and now we are in a position to find the connection between continuous functions and convergent sequences. So let us see a statement of this theorem. So take two topological spaces x and y. These are arbitrary topological spaces and not necessarily metric spaces. And this function, if this function is continuous, then for every convergent sequence xn that converges to some point x in x, the sequence fxn converges to fx. So in this sense, we have limit of fxn as n tends to infinity is equal to f of the limit of xn as n tends to infinity. So this is what it is said here. So, and the converse holds if x is metrizable. Again, the metrizability plays an important role to conclude the converse of this statement. So let us see a proof. So for this, let us suppose that f is a continuous function, and we have to show that given any sequence xn converging to x in x, the sequence fxn converges to fx in y. So to show this, let V be a neighborhood of fx in y, and this implies that f inverse V is a neighborhood of x in x, and this implies that since xn converges to x, there exists a capital N belonging to n such that xn belongs to f inverse V for all n greater than or equal to this capital N. But this implies that f of xn belongs to V for all n greater than or equal to capital N, and this is what we needed to show, that fxn converges to fx. So for each V, a neighborhood of fx, we found a capital N for which fxn belongs to V for all n greater than or equal to capital N. So this proves the first part of the theorem. For the converse, assume that the relation with the sequences, which we denoted as star above. So this is the relation, star relation. So this is satisfied. Assume star is satisfied. And now we have to show that f is continuous from x to y, and we will show that given any a subset of x, f of a closure is a subset of f a closure. So this was one of the equivalent characterizations of continuity that we proved before, and now we will use the sequence lemma to do this. So suppose that let y belong to f of a closure. This means that there exists a point x in a closure such that fx equals y, right? And because x belongs to a closure and x is metrizable, so here x is assumed metrizable, by the sequence lemma, there exists a sequence xn in A such that xn converges to x. And by hypothesis, this means that, so this is again the use of this relation star. This means that f of xn converges to f of x in y, and now since f of xn belongs to f of a for all n in n, this means that f of x belongs to the closure of f of a, because this is again a consequence of the first part of the sequence lemma by the sequence lemma again, and this means that f of a closure is a subset of f a closure. So here note that metrizability of y, is not required. Okay, so we have proved equivalent definitions of continuity of a function in matrix spaces. So first we proved the epsilon delta continuity, and now we have shown the connection with limits of sequences or limits of convergent sequences when we have matrix spaces or metrizable spaces. So this concludes our discussion of continuous functions, and we will move on to a new topic on connected spaces in the next week.